In Chapter 7, we're going to look at the quantum mechanical model of an atom. And quantum mechanics is when we're looking at things on a very, very small scale. And because they're so small, they behave differently than we would expect in our macroscopic world. Before we start talking about electrons, we're going to look at light, which is something that we are more familiar with, and the properties of light, and then we will look at electrons and the properties of electrons. As always, there are some suggested problems that you can look at the end of the chapter in your book. So you should be able to answer these problems by the time we finish the chapter. So let's look at light. Well, light exists as a wave. And the waves, and it's a form of electromagnetic radiation. It's composed of waves that travel in an electric field and also in a magnetic field. Because it is electromagnetic radiation, it travels through space at the same constant speed, and in a vacuum, that speed of light is 3.00 times 10 to the 8th meters per second. Now, if we take it out to more significant figures, that number changes just a little bit, but for our purposes, we can round it to 3.00 times 10 to the 8th meters per second for the speed of light. This gets represented by a constant c. And you may already know that the speed of light is c because there's a very famous equation, E equals mc squared. So E is energy, m is mass, and c is the speed of light squared. This will be something that if you continue on into future semesters, when we look at nuclear chemistry, this is a very important equation. So we're pretty familiar with light. Our lives are bathed in light. You've probably experienced a thunderstorm before, and you know that when the thunderstorm is away from you, you will see the lightning before you hear the thunder. So the lightning travels at, because it's light, 3 times 10 to the 8th meters per second, but it takes much longer for the sound to get to us. So sound is a wave also, and it travels at 340 meters per second. So why would there be a difference between the light waves and the sound waves? Well, the reason is because light is an electromagnetic wave, so it travels at a much faster speed. Sound is not, and so sound is the waves that are traveling through the air, so the crest and trough of the air molecules as they travel to get to you. And so it travels at a much slower speed. So it's delayed by about 5 seconds for every mile between you and where the lightning strikes. We need to have some different ways that we measure our wave in order to describe it. So one of the measurements that we can take is called the amplitude. We measure the amplitude between a line that runs through the center of the wave and the crest of the wave. So the very top of the curve is called the crest. That difference is what we refer to as the amplitude. If the amplitude changes, that changes the brightness of our light. Another measurement we take is from the top of one crest to the top of the next crest. And this is called the wavelength. We represent this with the symbol lambda. Now, this isn't the only way that we can measure the wavelength. We can also measure from where the wave crosses that center line, this is called a node, to the second node that we cross. This is the same distance. This would still be lambda. So there's different points in which we can measure. Another way we could measure would be from the trough. So trough is the lowest part of the wave, from one trough to the next. Again, we would get the same measurement, lambda, but another way that we could measure. There is yet another measurement we can take, and this is called frequency. Frequency is represented by the Greek letter nu. And this is the number of waves that pass a given point in a period of time. And so the measurement for frequency is waves per time. So if we're talking about per second, so cycles per second, this is what we call a hertz, abbreviated Hz, or 1 over seconds. So that seconds to the -1, that's like we're seconds in the denominator. And this is the frequency. So this is how fast the waves are passing you. So if to relate this to something that you might have experience with, if you've ever been at the ocean or a beach with waves, so the frequency would be how fast the waves are hitting you as they're coming to shore. So our total energy is proportional to both the height of the wave and the frequency of the wave. So the larger the amplitude, the more force it has. So if you've ever been at a beach and been knocked over by a big wave, that means that it has more energy because it's taller. Also, the more frequently the waves come, the more force that they have as well. Now, there is a relationship between the wavelength and the frequency. They are related to each other, and they're related by the speed that they're traveling. So the shorter the wavelength, the more frequently they're going to come past you. The longer the wavelength, the less frequently they're going to come past you because they're traveling the same speed. So these are inversely proportional to each other. The wavelength, which we label lambda, measured in units of length, and the frequency, which is nu, measured in cycles per second, or 1 over seconds. Okay. These are inversely proportional. Because we know the speed of light and it's constant, we can find the frequency or the wavelength, depending on what we have. And most commonly, I write this formula as C equals lambda nu. So what's written here is just a rearrangement of that. So if we have the speed of light, the units of speed of light are meters per second. The wavelength needs to be in meters, and the frequency is going to be 1 over seconds. It might be labeled as hertz. So just so you recognize that hertz means 1 over seconds. So let's try an example. Let's calculate the wavelength of red light that has a frequency of 4.62 times 10 to the 14th hertz. So we are going to use our equation, C equals lambda nu. We know the speed of light is a constant. We are trying to find the wavelength, so we're going to rearrange this. C is speed of light divided by the frequency. The speed of light is 3.00 times 10 to the 8th meters per second. And our frequency is given to us, 4.62 times 10 to the 14th per second. Our per seconds are going to cancel, and we're going to end up with meters. Oops. Let's try that again. So 6.49 times 10 to the negative 7th meters. Now this is a very small measurement, right? 10 to the negative 7th meters is very small. So frequently when we report visible light that has color that we can see, we will convert the wavelength into a easier to use unit of nanometers. Okay, so now our number gets much more easy to handle. 6.49 times 10 to the second nanometers, which is just 649 nanometers. So when we're reporting visible light, you will frequently see it in the hundreds of nanometers range. Here's one for you to try. Pause the video and try to calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. So this 100.7, that's the carrier frequency. So the number you turn to on your radio dial, that is the number in megahertz. All right, so megahertz, when we're using our equation, we need to be in hertz. So we need to do a conversion first. 100.7 megahertz into hertz. So 1 megahertz, mega means million, so it's 10 to the 6th hertz in a megahertz. So we get 1.007 times 10 to the 8th hertz. And remember, a hertz just means 1 over seconds. So now we can use our equation. We're trying to calculate the wavelength, which is lambda. So we would do lambda is equal to speed of light divided by the frequency. So 3.0 times 10 to the 8th, that's our constant for the speed of light, divided by our frequency, which we just converted to hertz, or to 1 over seconds. Our seconds cancel, we'll be left with meters. We get 2.98 meters. So think about this. So this is the carrier frequency for our radio station, 2.98 meters. This is about approximately 9 feet long is the wavelength for the radio signal. Much, much longer than what we saw for our visible light. So remember, our amplitude is a measure of how bright or dim the light is. So different amplitudes are different brightnesses. If we change the wavelength, then we are changing colors. So our blue light has a much shorter wavelength. Okay, yellow-green wavelength is in the middle, and red is a much longer wavelength. So by changing and varying those wavelengths, we're changing the color of light, but also if we change it very large amounts, it's the type of electromagnetic radiation that we are observing.